Hey everybody, Dr. Bennington here. Welcome to the review of igneous rocks. Now, if we think about the rock cycle, which describes how rocks are formed and then how rock material is cycled through the lithosphere of the Earth, we notice that igneous rocks are sort of the ultimate origin of all rocks. Igneous rocks start out as molten rock, magma, which ultimately comes from the upper part of the Earth's mantle, from the asthenosphere. As magma from the asthenosphere works its way up through the lithosphere, it can melt the rock that's already in the lithosphere and create additional magmas. There are several different types of magma that are generated in the asthenosphere and the lithosphere of the Earth. But however you make the magma, eventually it reaches the crust of the Earth, where it solidifies in the interior to form plutonic or intrusive rocks, or it erupts on the exterior, on the surface of the Earth, to form extrusive or volcanic rocks. Now, like all rocks, igneous rocks are classified named using two sets of criteria. We look at the mineral composition of the rock, and then we look at the texture of the rock. Now, for igneous rocks, the mineral composition is silicate minerals. So the silicate or the rock-forming minerals are the major components of igneous rock. Minerals that you've all seen in lab: quartz, the feldspars, albite, K-feldspar, labradorite. Hornblende and augite, the two very similar chain silicate minerals. Olivine, the kind of olive green silicate mineral. And then the mica minerals, biotite and moscovite, are commonly present in igneous rocks in smaller quantities. So the silicate or rock-forming minerals are the major minerals found in igneous rocks. But they occur in igneous rocks in a particular pattern, which is useful to keep in mind. Magmas that begin in the mantle of the Earth are very rich in iron and magnesium, and the crystals of mineral that initially start to form from these magmas are also rich in these elements, and they form what we call mafic minerals, Ma for magnesium, F for iron. And these minerals tend to be dark in color, and so magmas that originate in the upper mantle of the Earth form dark-colored rocks, what we call mafic rocks. If you take mafic rocks and you remelt them, you can, or if you melt igneous rock in the mantle in the presence of water, you can cook off a magma that is less rich in iron and magnesium and more rich in silica. And those types of magmas tend to be to form minerals that, like labradorite, feldspar minerals mixed with minerals like hornblende and augite and olivine. And so those magmas produce what we call intermediate rocks, which tend to be a kind of a combination of the lighter colored feldspar minerals and the darker colored chain silicates and olivine. And then magmas that are produced by the remelting of intermediate rocks in the crust of the Earth produce magmas that are very rich in silica, and silica-rich magmas tend to produce rocks that have a lot of quartz and the lighter colored feldspars like albite and K-feldspar. And those minerals produce felsic igneous rocks, which tend to be less dense and lighter in color than intermediate and mafic rocks. Now, when it comes to igneous textures, texture is primarily controlled by the cooling rate. Magmas or lavas magmas that cool very slowly, and by very slowly I mean over thousands, tens of thousands, hundreds of thousands, even millions of years, produce rocks that have very, very large crystals. So the longer magma has to develop crystals, the larger individual crystals can become, and they can grow large enough to be seen with the naked eye. And that produces a texture that we call phaneritic. So in a phaneritic rock, it's very easy to see individual crystals. You can see their shapes. You can see that you have different colored crystals in the rock. And if you turn the rock in the light, kind of rotate it around, you can usually see the cleavage planes in minerals like feldspars, hornblende, augite, where the rock is broken. So flashy cleavage planes and distinct crystal outlines are characteristic of phaneritic rocks. The opposite of phaneritic is aphanitic, and in aphanitic igneous rocks, the magma or lava cools so quickly that individual crystals don't have much time to get very large, and instead you end up with many, many, many microscopic crystals. And this produces a texture which is very sort of dull looking. You don't see flashy cleavage planes because the mineral crystals are microscopic, so you have a very sort of dull-looking rock. You may see a few shiny, flashy individual crystals kind of floating around in the dull background, but the majority of the rock has a dull, non-flashy appearance. And then there's sort of an intermediate condition. It's not unusual in certain types of igneous rocks for the magma to start out cooling very slowly and for some large crystals to develop and kind of be floating around in the remaining liquid. And then the magma gets moved up towards the surface of the Earth or erupts onto the surface of the Earth as lava, and the remaining molten rock cools very quickly. So you get a mixture of phaneritic large crystals and aphanitic background, what's called the ground mass of the rock. And this produces a texture that we call porphyritic. So if you see two distinct crystal sizes, large crystals kind of floating in a dull background, that's a porphyritic texture. So let's look at some examples of common igneous rocks. We'll start with rhyolite. Rhyolite is an igneous rock that we don't have a lot of examples of in the eastern part of the country, but it's a fairly common rock out west, particularly in volcanic areas. So it's kind of a tan to reddish colored rock. It's fine-grained. It's aphanitic, so you don't see flashy cleavage surfaces covering the rock. But if you look carefully, it's very common to see embedded within the dull ground mass little flashy crystals of mineral. And you also may see vesicles, which are holes or spaces in the rock produced by gas bubbles that were in the lava as it was solidifying. So let's take a look at an example of a rhyolite specimen. And if you look carefully at the specimen, you can see first that there are a lot of empty spaces, kind of flattened vesicles, and some are large and some are very small. And then you can also see some flashy crystals as well as the rock is rotated. So there are a few bits and pieces of quartz crystals within the body of the rock, and the well-formed crystals and the vesicles are a really good indication that this is an igneous rock. And the overall light color of the igneous rock suggests that it's a felsic igneous rock. So a felsic fine-grained igneous rock is very commonly a rhyolite. The phaneritic sort of brother of an aphanitic rhyolite is a granite. So if the magma that erupts on the surface to produce a rhyolite sits deep in the crust of the Earth and cools over a very long period of time, the same minerals will form, but they will form crystals that are macroscopic, that are visible to the eye. And typically what you see in granites are crystals of quartz, crystals of either albite or K feldspar or some combination of the two. And then there's usually some dark mineral kind of sprinkled in, either hornblende or maybe some biotite mica. Granites, if you turn the specimen in the light, so let's pull up a specimen here and take a look at it. So if you take a look at a granite, you can see individual crystals of mineral within the rock. The gray crystals, which look kind of like bits of broken glass, are quartz, and then the pink and lighter colored mineral is the feldspar. And if you look carefully as you turn the rock in the light, you can see the feldspars flashing at you. Their cleavage planes flashing when they reflect the light. There isn't a whole lot of dark mineral in this particular specimen of granite, just a little bit of a few grains of darker mineral, probably hornblende. Okay, let's look at an example of a porphyritic rock and also an intermediate rock. As I said before, intermediate rocks contain a mix of the lighter, less dense and lighter in color felsic minerals and the darker in color, more dense mafic minerals. So the typical intermediate rock is an andesite. And andesites very commonly occur as porphyries. So a typical andesite specimen has a porphyritic texture where you see large crystals floating in a dull ground mass, and the matrix or the ground mass of the rock is usually kind of a gray or grayish green or maybe a tan color. So it's not too light and it's not too dark. Again, it's a mix of both light and dark minerals together. If we pull up a specimen here of an andesite porphyry, you can see in this specimen very, very nice examples of hornblende crystals, these kind of elongate prism-like crystals, and then the white crystals are feldspars. And so you have the sort of salt and pepper hornblende and feldspars floating around in a dull ground mass that's gray, which is kind of the mix of the two colors of crystals. Now, the phaneritic version of an andesite or an andesite porphyry is a diorite. So in a diorite, all of the crystals are large and visible to the naked eye. So you have a rock that is composed of lighter colored feldspars and darker colored hornblende usually, and that creates a very sort of salt and pepper appearance. If we bring up a specimen here of diorite, you can see that sort of even mix of light and dark, salt and pepper. And then as you turn the specimen in the light, you see lots of flashy cleavage planes because both feldspar and hornblende have two good directions of cleavage that are revealed on the broken surfaces of the rock. Now we're moving to the mafic end of the spectrum. One of the most common rocks on Earth, and indeed probably the most common rock in the crust of all of the rocky planets, is basalt. Basalt is what you get when you take magma from the upper mantle of a rocky planet and you let it erupt near the surface or out onto the surface, and it crystallizes relatively quickly, producing lots of microscopic crystals made up of hornblende and augite and olivine. So what you end up with is a very dull-looking rock that's somewhere between dark gray to black in color, very high density. So basalts feel very heavy because of all the iron in those minerals. Basalts are also very hard, very difficult to break. You hit them with a hammer, the hammer just tends to bounce off. Now, like any aphanitic igneous rock, if you look very carefully, you might see a few scattered crystals that manage to, grow large enough to be seen, and maybe a vesicle or two. So small crystals and vesicles are a good indication that you're looking at an igneous rock. So let's pull up an example of a basalt here. So you have a kind of a dark gray color, and you can see these little tiny holes in the rock are vesicles. And then maybe you catch a flash here and there from a stray crystal floating around in the matrix of the rock. Now the phaneritic version of a basalt is called a gabbro. So if the magma that would produce a basalt, if it erupted up towards the surface or onto the surface, if that magma is allowed to crystallize very slowly deep below the surface, you will produce a phaneritic rock that has the same minerals as a basalt, hornblende, augite, and olivine, but with that phaneritic texture with very, very flashy crystals. Just like a basalt, gabbros are very dense, they're heavy, and they're relatively dark in color. So here's an example of a gabbro, and what you look for is turning the specimen in the light. It's very flashy looking. You're seeing lots of cleavage planes. There pretty much isn't a part of the surface of this specimen that won't kind of wink at you if you get it at the right angle in the light. So that very sort of random distribution of flashy cleavage planes is a good visual indication of a phaneritic igneous rock. And the dark color tells you that it's a mafic rock, or mafic rock. Not sure how you pronounce it, mafic. Probably the English say mafic, we say mafic. But anyway, mafic texture, or I'm sorry, a mafic mineral composition composed of predominantly dark minerals. And then a few odds and ends. These are examples of common volcanic rocks. These are rocks produced by lavas that erupt onto the surface of the Earth. So a very common type of volcanic rock is a scoria. Scorias are very easy to identify. They're very porous because they have lots and lots of vesicles. The composition of the rock is usually basalt, although you can also have rhyolitic scorias. But what gives a scoria away is its very, very bubbly looking or porous texture. Scorias tend not to be very dense. You've probably all seen a scoria if you've ever looked inside of a gas barbecue. The stone at the bottom around the burners in the barbecue is typically scoria. The scorias can be reddish brown, they can be gray, they can be black in color, depending on a lot of conditions in the lava that solidified into the scoria. Here's an example of a kind of a reddish looking scoria. It's got lots of oxidized iron in it. And you turn it and you can see it's very, very porous. So just a very sort of spongy looking rock. Probably everyone's favorite volcanic rock is obsidian because it's so beautiful. Obsidian is basically volcanic glass. It is produced from very silica-rich magmas that cool so quickly that mineral crystals don't have time to form, and instead the silicate ions basically are frozen in an almost liquid state, which produces a glass. Physicists refer to a glass as a rigid liquid. So if you have a rock that looks like it's a chunk of glass, it might be a piece of obsidian. Let's pull up a specimen here. So what you look for a freshly broken surface, and if you see these sort of concentric, kind of dished out fracture patterns, that's called a conchoidal fracture. That's very, very typical of glass. It's the way glass breaks. It's very typical of obsidian. You have to be careful handling obsidian because very often obsidian has very, very sharp edges. So that's another thing to look for. You can cut yourself if you run your finger. You can chip obsidian down to a razor sharp edge. And then finally, if you take a lava that would cool to form a glass, but you froth it up with a lot of gas bubbling out of that lava, you will produce pumice. And I know pumice was not one of the specimens that was included in the rock hits, but it's worth mentioning. It's very distinctive, very, very light weight, very, very low density. In fact, pumice, most pumice will float. It's very light in color. It's very abrasive. So it's pretty easy to recognize. And let's just pull up a specimen here. Right, so very low density. If you look very, very carefully, you can see its glassy texture. It's like a frothy glass. And as I said, if you put pieces of pumice in water, they will float. And you find pumice washing up on beaches all over the world, especially in the Pacific region, because stratovolcano eruptions produce pumice, and then the pumice just floats on the waves and the currents and can wash up pretty much anywhere around the world. All right, that's it for igneous rocks. Thank you for watching, and I hope you found that helpful.